For our physics media project, we chose the topic of sound waves on a guitar. The objective of our project is to demonstrate fundamental frequency through utilization of strings on a guitar. Fundamental frequency is the lowest frequency produced in a group of harmonically related frequencies. When one wavelength is equal to one period in related harmonic sequence, that is fundamental frequency. Guitars have 6 fundamental frequencies, E being 82 Hz, A being 100 Hz, D being 147 Hz, G being 196 Hz, B being 247 Hz, and E being 330 Hz. Once frets are pressed on a guitar, varying wavelengths/frequencies occur in the form of second or third harmonics. The first, sometimes called the second harmonic, is half the length of the fundamental frequency. The third harmonic will be 1/3 the length, and the fifth harmonic will be 1/5 the length, and so on. First, the total length of each guitar string was measured to calculate the linear density. The vibrating length of the string and the mass of the string is also measured to calculate wave velocity. Next, an acoustic guitar was taken and tuned properly so that each string was in equilibrium. The frequency for each string was measured for later calculations. Then, a constant weight was hung from the strings and the distance from the equilibrium point was measured in order to calculate the tension on the string. And lastly, the theoretical and actual velocity of the wave was calculated and compared. Our prediction/hypothesis is given a constant mass on a given string. The linear density and tension will directly affect the frequency played on a guitar string. The actual speed of sound wave calculated from the string will have little discrepancy from the theoretical speed due to environmental and instrumental errors. The equation for fundamental frequency is f of 0 is equal to the square root of the tension divided by the mass of the string multiplied by the total length of the string, all divided by 2 times the length of the string. The equation for tension is equal to force multiplied by the vibrating length of the string divided by 4 multiplied by the displacement of the string. The equation for theoretical speed is velocity is equal to the square root of tension divided by the linear density, which is equivalent to the mass of the string multiplied by the total length of the string. The equation for actual speed is velocity is equal to the measured frequency multiplied by the wavelength, which is equal to 2 multiplied by the vibrating string length. String E low. String A. String D. String G. String B. String E high. Here are the results for the linear density, tension, and vibrating length. Here is the theoretical speed, theoretical frequency, actual speed, and discrepancy. Lastly, here is a comparison between the fundamental/theoretical frequency and measured frequency. In conclusion, it was determined that the linear density and tension do in fact directly affect the frequency produced by the string. More specifically, the relationship of either variable is inversely proportional to that of the fundamental frequency produced. The results of the experiment show that there was very little discrepancy between theoretical speed and actual speed of strings A and E low. However, for strings E high, B, G, and D, there was up to 36% discrepancy. This discrepancy resulted in the calculated fundamental frequency of those 4 strings to vary greatly from the measured frequency observed. An explanation for the error is that the guitar used in this experiment has a crooked bridge.